Once again, I welcome you for NPTEL course on fractals and multifractals. In the last lecture, we have constructed some nice Euclidean geometrical structure which possess some complex natures. For instance, Cantor set, Van Koch curve, Sierpinski triangle. These three Euclidean objects have some complex structures. In Cantor set, it has the infinite number of points and it has a measure 0. In the Sierpinski triangle, it has 0 area and the boundary has infinite length, whereas in the Van Koch curve it has a infinite length. One can observe that all these Euclidean objects are defined through iterative process. Professor Benoit B. Mandelbrot observed that these Euclidean object as well as some naturally appearing objects also possess two main property, that is non-integer dimension and self-similar property. Based on that, the concept of non-integer dimension and self-similarity extensively seen in the nature object sparked of Mandelbrot to coin the word fractal, derived from the Latin adjective fractals, meaning broken or fragmented. So, this original fractal is derived from the Latin word fractus. So, he coined this name in the early years of 80s, whereas the Cantor set, Sierpinski triangle and Van Koch curve all are already defined or well known to all mathematicians. But he observed that these two specific property, non-integer dimension, we may come across the integer dimension well known for everyone, but he observed that non-integer dimension property of all these three objects and self-similar property. So, based on these two property, Mandelbrot defining fractal as follows. First one, Professor Benoit Mandelbrot defined the fractal to be a set with the Hausdorff dimension strictly exceeds its topological dimension. Suppose once want to say some object is a fractal object, we need to find the Hausdorff dimension and topological dimension of the object, then compare the two dimensions. If Hausdorff dimension is strictly greater than the topological dimension, then one can say the object is a fractal object. Also, he later proposed the new definition for a fractal. A fractal is a shape made of parts similar to the whole in some way. This definition is given by based on the self-similar property. So, a shape made of parts similar to the whole in some way. Here, this some way is a keynote. Based on this, the some way, that in the sense the shape of the part similar to the whole in some way. There are two possible ways. One is a part exactly resembles the whole, another one a part approximately resemble the whole. So, based on these two, the fractal is classified into two types. One is random fractal and other one is deterministic fractal or regular fractal. So, what do you mean by the random self similarity and exact self similarity? You can take one object, then take the part of that object, then if this part exactly match with the whole, then we can say the object has a exact self similar nature. Otherwise, if the part approximately resembles the whole, then it is called the approximate self similarity, then the corresponding object is called the random fractals. So, we already come across three Euclidean monsters: Cantor set, Sierpinski triangle and watch curve. Now, the question is whether these three objects will fall under this two definition. Before discussing the self similar nature and fractal dimension of these sets, the first definition is proposed by Professor Bernard Mandelbrot in his monumental book The Fractal Geometry of Nature in 1983, whereas this one is given in the lectures and it is available in the many reputed fractal books. If you want to, one can refer this first book to know more about the definition based on the fractal dimension. In the second part of this course, we are going to rigorously analyze the dimension theory. Now, let us try to explore the self similar nature of the well defined Euclidean object which we are discussed in the previous lectures. The first one is the Cantor set. So, what do you mean by the self similar property? Whether the part of the object resembles the whole or not. Now, here we have the some finite iterations. So, from this we have sketched the Cantor set graph. Now, one can observe that if you are taking this part, left side part, this one, and compare with the whole, again you can see we have the line segment and it is dividing two part and it is dividing two part and again each section is dividing two part. So, after the infinite iteration we will get the Cantor set. Now, you can look the whole thing. So, if you take any part of the Cantor set, it reflects the whole thing. Therefore, Cantor set follows the self similar property. Now, we will check the self similar property of Sierpinski triangle. Here, one can note that suppose I am taking the part, this part alone, and one can scale up, zoom in, then this part is exactly matching with this whole object. Also, we have take some smaller part, this one, if you are zoom in, then this part also exactly match with the whole thing. So, Sierpinski triangle also obeys the self similar property and will check the Van Koch curve. Now, for the Van Koch curve, if I take this part is exactly match with the whole thing, then this also obey the self similar property. Maybe we can take this part also resembles the whole thing. Now, the Van Koch curve and the Sierpinski triangle and the Cantor set. If you observed, if you are taking any small part, the small part is exactly resembles the whole thing. Therefore, these three objects are example for the self similar object more precisely, it has the exact self similarity. Therefore, these are all the example for the regular fractal or deterministic fractal. Then one can ask, then what is the example for the random fractal? Most of the random fractals appears in the natures. Here you can see there are 4 images were presented here. The fan leaf and lightning in the second figure, and here branches of a tree and a broccoli. Now you can check this fan leaf. If you are taking this part alone, then this not exactly, somehow it is resembles the whole thing. Or if one can take this part, then this part also resembles the whole thing in some sense. Therefore, this fan leaf follows the approximate self similarity. Whereas if you come to the lightning, we may take this part, and this part, if you compare with the whole, it resembles the approximately on the whole thing. Therefore, this is also example of a approximate self similarity. And here branches of a tree, maybe we can take this branch. Here this branch is approximately resemble the whole thing. Therefore, this also example for the approximate self similarity. In the broccoli, I take this part, one can compare the part of this broccoli with the whole thing. This part also approximately resembles the whole things. That means the sizes are different, their natures looks like similar. So, therefore, these 4 objects are the example for the random fractals. Then these fractals has some irregular nature compared with the deterministic fractals. Okay. So, based on the self similar property, we define the fractal into 2 types. One is regular and random fractal. Random fractal appears in mostly in the nature. The regular fractal is also known as the deterministic fractals. Based on this, Falconer suggested the following property which guarantees a set to be a fractals. There are 5 properties. Then a fractal exhibits a fine structure at arbitrary small scale. That means if you are zoom in or zoom out, their structure is well structured. That means the fine structure. Nearly the same at every corner on a large scale and on a small scale. When you zoom in and zoom out, then the resemblance will be there. That be the part will be resembles the whole thing. Further, no smooth part should be observed by scaling. This is very important. It has a self similar nature, but no smooth part should be observed by scaling. For example, if you are taking the unit line interval, if you consider this as a midpoint, then if you are break by 1 by 2, if you are consider this part, and this part is exactly similar with the unit interval, whereas whenever you are zoom in and zoom out, this object has a smooth parts, whereas in the fractals it has the self similar property. If you are zoom in and zoom out, you will not find the smooth part. So, this is main difference between the Euclidean self similarity and fractal self similarity. And the second property, the fractal has a Hausdorff dimension, that is in general strictly greater than the topological dimension, which is already defined by the Professor Benoit Mandelbrot. Then it is recursively defined through initiators. Fractal is finite, sometimes infinite copy of itself. In general, fractal is too irregular to describe in the traditional geometry. So, if this property guarantees that a set to be a fractals. So, these properties are presented in the reference given here, Kenneth Falconer, Fractal Geometry, Mathematical Foundation and Application in the 2014 edition. Next. Now, Professor Mandelbrot defined the fractal in the two way, with respect to self-similar property, that means with respect to their pattern, and with respect to the dimension theory. In the dimension theory, we need to find the Hausdorff dimension and topological dimension for an object to verify whether the object is a fractal object or not. So, now let us try to find fractal dimension of already defined complex structure objects, Cantor set, Sierpinski triangle and Van Koch curve. So, let me give the glimpse of the fractal dimensions. Maybe the rigorous analysis and rigorous mathematical tool will discuss in the second half of the course, whereas here I give the glimpse of the fractal dimensions. Let S be a non-empty set, any non-empty set, and n of delta denote the number of boxes required to cover the object S with size delta. So, what it means? We need to take a non-empty set and take the small boxes of size delta and cover the object by these small boxes, then count the number of boxes is required to cover the object, that here we denoted as n of delta. So, n of delta denote the number of boxes needed to cover the set S with size delta. For instance, if you consider the line here 0 and 1, this line segment, if I take the boxes, so what do you mean by the boxes here? Boxes is a mathematical object which has sometimes it has a length alone, sometimes height and length, sometimes it is three-dimensional object, it has a height, breadth as well as the length. So, here boxes refers the common terminologies. So, here 0, 1 is considered in the real number system, subset of a real number systems. If I want to cover this one, so I can take a box size delta as 1 by 2, then I need a two closed interval with the two closed interval 0, 1 by 2 union 1 by 2, 1 will cover this interval. So, how many number of boxes we need? We need two boxes of size 1 by delta. So, this is the n of delta is 2 and size of the boxes is 1 by 2. But one can observe from this one, if delta is 1 by 2, I need two boxes to cover this object. Suppose if I fix delta is as 1 by 4, then I need here and one more here, this is 1 by 4, this is 2 by 4 which is equal to 1 by 2 and here 3 by 4. So, if I take delta as 1 by 4, then for covering the same object we need 3 boxes 0, 1 by 4 union 1 by 4, 1 by 2 union 1 by 2, 3 by 4 and union 3 by 4, 1. This 4 box, if you are taking the union of 4 boxes, it covers the object 0, 1. So, if delta is 1 by 2, we need 2 boxes, number of boxes, that means n of delta is 2. If I fix delta as 1 by 4, then n of delta is 1, 2, 3, 4. So, the relation between the delta and n of delta is whenever you are reduce the box sizes, the number of box required to cover the object will increase. See here, if you fix delta is 1 by 2, we need only 2 object to cover the line segment, whereas if you are taking delta equal to 1 by 4, we need 4 boxes to cover the given object. So, whenever this delta is decreasing, then n of delta will increase. That means this n of delta is indirectly proportional to the delta. Whenever delta is decreasing, n of delta will increase. Whenever delta is increasing, n of delta will decrease. So, this relation is given by the formula n of delta is indirectionally proportional to the 1 by delta power d. So, what do you mean by this d? For this, suppose I am taking the one dimensional object, I am taking the line segment in the real number. Then for, as we discussed previously, if whenever the box sizes are decreasing, then n of delta will increase. So, this is the one dimensional object, therefore, n of delta is indirectly proportional to delta power minus 1. Suppose I am taking one object in r power 2 like this square. If I take delta equal to 1 by 2, then of consider all the size are equal, then if you are taking delta equal to 1 by 2, then we need 4 boxes to cover this object. That means and n of delta is indirectly proportional to delta power minus 2. If you are considering any object in the space and the sense r power 3 like this type of some zigzag object, if you are taking deltas ops and then number of delta n of delta will increase, then the relation between r in r power 3 n of delta and delta is n of delta is indirectly proportional to delta power minus 3. Then what do you mean by this delta? Sorry, what do you mean by this number d? D stands for the dimension of the object. So, here n of delta and delta power minus d is an inverse relations. Now, if you want to solve this one, it is a simple mathematics. You can take logarithmic on both sides. Then, if you are taking logarithmic, we will get the logarithmic constant log c plus log of delta power minus d. So, which can be, our notion is we need to find the capital D. So, for finding the D, so D can be written as ln of n of delta. So, there is a, if you are get this side, it will get ln C, then again there is one minus here, while going it will get plus, and this will become minus, and over ln delta, right. Then if you are finding the D, minus ln n of delta over ln delta plus ln C by natural logarithm of delta. So, here whenever delta is increasing or decreasing, n of delta either increase or decrease based on the delta. We have both the inverse relation. Okay. Now, the C is the constant number. Whenever this delta approaches to 0, this quantity will be equals to 0, or we ignore this term. So, D, if limit delta tends to 0, ln n of delta, this can be minus, you can come to the denominator, ln delta power minus 1. So, why we are taking the delta tends to 0? If you want to perfect cover, whenever this box sizes are decreasing, we can find the finer approximation for the object, or will able to find the better result for finding the size of an object. So, whenever this delta tends to 0, this term becomes 0 and we will get this one. So, this D usually we can call as the box counting dimension or fractal dimension. This D one can call as the box counting dimension or fractal dimensions. Now, how to find the box counting dimension of an object? Since for any non-empty set we can find the box counting dimension, then what is the box counting dimension of the line segment 0 and 1? 0 and 1. Suppose I am taking delta as 1 by 2. As we discussed previously, then we need 2 closed interval to cover this box. So, here the boxes means closed interval. In this is the subset in R. So, here what do you mean by the boxes? Box mean the closed intervals. Then the n of delta is the number of boxes required to cover the closed interval 0, 1 is 2. Then if you finding as per this definition, for time being we can ignore the limiting case. If you find the D value, it is equal to ln n of delta. So, ln 2 over ln 1 by 2, sorry, ln 1 over 1 by 2, 1 over 1 by 2. So, which is equal to ln 2 by ln 2, which equals 1. So, we can say that the box counting dimension of this object is 1. Suppose I change this delta. If I change this delta as 1 by 4, then what will happen? So, this line, if I change delta as 1 by 4, then we need 1 by 4, 1 by 2, 3 by 4. Now, we have 3 boxes By using 3 boxes, one can cover this whole interval 0, 1. So, the number of boxes required to cover this interval or line segment is 4. Now, if you are finding the dimension, box counting dimension, ln of number of boxes, 4 boxes over ln of 1 over delta. So, 1 over delta in the sense 1 over 1 by 4 will get 4. So, which equals ln of 2 power 2 over ln of 2 power 2. So, one can get 2 ln 2 by 2 ln 2, which again is equal to 1. So, whenever if you are choosing different delta, here we are choosing deltas 1 by 2, the number of boxes is 2. If you are choosing deltas 1 by 4, here number of boxes we are getting as 4. If this is decreasing, the number of boxes required to cover the object is increasing, whereas the dimension is still the same. So, with respect to the delta, the dimension is never changes. Okay. So, in the case of delta, if you are decreasing the delta tends to 0, then one can conclude that if you are choosing one object in the real number system, 0, 1 has the box counting dimension 1 if you are choosing any delta. Now, if I choose then object from the r power 2, if I choose the object from the r power 2, say for example, I am choosing this unit square, all sides are equals 1 unit. Then similar like this example, shall I take delta as 1 by 2? Yes, if delta is 1 by 2, then we need to calculate the number of boxes is required to cover this object. Now, again you can join the midpoints, then we have this one. So, here what you mean by the boxes? So, in this case box mean the closed interval, because the object is embedded in our real number system, whereas here object is embedded in the space r power 2. So, boxes in the sense we are taking the squares. So, the number of boxes required to, how many boxes we need? Smaller squares 1, 2, 3, 4. We need 4 boxes of size 1 by 2 to cover this unit square. Now, what is the d? D is ln 4, we can write 2 power 2, then ln 2. So, which equals 2 times ln 2 by ln 2 equals 2. So, the box counting dimension of or fractal dimension of the unit square is 2. Similarly, if you are taking delta as 1 by 4, then you can see this box. If you are taking 1 by 4, 1, 2, 3, and here we need 1, 2, 3, 1, 2, 3, 1, 2, 3. So, we need how many boxes? 8 boxes, here 8 boxes, and here 1, 2, 3, 4, 5, 6, 7, 8, and here 8 boxes. Totally we need n of delta as in 16. When you are choosing delta as 1 by 4, then number of boxes required to cover this unit square is 16. If you are finding the fractal dimension for this one, again you will get 16, we can write 4 power 2, and here ln 4, again you will get 2 times ln 4 by ln 4, then one can get again the fractal dimension is same. That means here for finding the box counting dimension of this unit interval, whenever this delta is changing, this is invariant with respect to the delta. Same pattern follows in the r power 2 also. So, here if you are taking any regular object in the r power 2, if you are finding the box counting dimension, it is equal to 2. Now, as I mentioned, if you are taking any Euclidean object, it obviously possesses the self similar property. Now, what is the difference? It has the self similar property. Also, if you are finding the fractal dimension or the box counting dimension, will get the integer values, Say for example, for this unit line we obtained the box counting dimension which is equal to 1, then it has obvious self similar nature. You can take this part and this part is exactly similar to the whole. Then this object box counting fractal dimension is 1, whereas it has a self similar property. So, as per the definition of fractals, the topological dimension must be less than the Hausdorff dimension, then we can call the object as the fractal object. Whereas here for defining the fractal in term of fractal dimension, I am giving this alternative idea. That means you can take the set S, assume that this set is embedded in some space E, then find the box counting dimension D of this set S and find the box counting dimension of this embedded space E. Whenever the dimension, that means dimension in the sense the fractal dimension of the set is strictly less than the embedded space dimension, then we can call this object as a fractal object. As per this definition, if you are seeing this line possesses the self similar property, whereas its fractal dimension is 1. Obviously, this is embedded in R. One can find the, by using this terminology, the real number system has the box counting dimension as 1. So, we cannot say this object is a fractal object. In the similar way, we can find the R, we can estimate the fractal dimension of any object in R power 2. If your object is regular object like the square, circles, etc., if you are finding the box counting dimension, it will be the integer which is equal to the dimension of the space, embedded space. So, for defining the fractal without Hausdorff and topological dimension, we can use the box counting dimension to conclude that whether the given object is fractal or not a fractals. For that, you need to find the fractal dimension of an object and fractal dimension of the object where it is embedded. If embedded space fractal dimension and the object fractal dimension, you can compare. If this is lesser than this dimension, then you can conclude that the object is an fractal object. Otherwise, we cannot say it is an fractal object. So, we already noted that Sierpinski triangle, Van Koch curve and Cantor set has a self-similar property. Shall we try to find the fractal dimension of this object and examines whether these possess the non-integer box counting dimensions. Let me try to find the fractal dimension of Cantor set. So, here the Cantor set, this construction process we already discussed in the previous lectures. Now, one can observe that in the 0, 1 we are dividing 3 equal parts and removing the mid interval, open interval we are removing. And after the first iteration we have 2 interval of size 1/3. So, to cover this object in the C1, for covering C1 we need a 2 interval 0 and 1/3 and 2/3, 1. By using these two objects we can cover the set C1. This is C0, we can cover the C1. Suppose if you are taking delta as 1/3, then the number of boxes required to cover C1 is 2. That means n of delta is 2. If you are finding the fractal dimension for here, that means box counting dimension here, which is equals ln of 2 by ln of 1 over 1/3, which is equal to ln 2 by ln 3. Whereas in the second iteration in the C2, if you apply the same procedure, it has 1, 2, 3, 4 intervals of length 1/3 power 2. So, if you are finding the fractal dimension, one can get ln 2 power 2 over ln 3 power 2. So, again if we are by the property of ln, the powers will cancel when it comes to the front, then we will get ln 2 by ln 3. In the second iteration, the fractal dimension is ln 2 by ln 3, and third iteration, in the first and second iteration, both the d values are ln 2 by ln 3. One can observe this is less than the value 1. If you are continuing this process, here also in the third step also, if you are finding, one can get, will get 2 power 3 interval of size 1/3 power 3. So, ln of, that means after the, in the third iteration here in the C3, 2 power 3 intervals, number of intervals of length 1/3 power 3. So, if you are taking 1/3 as common, then you will get 3 power 3. So, which is equal to ln 2 by ln 3. So, with respect to the iteration, this dimension is invariant. So, if you are taking after nth iteration, the Cantor set has 2 power n interval of size 3 power n. So, if you want to cover the Cantor set in the nth interval, we need 2 power n number of boxes of which size is 3 power n. That means, if you are taking delta as 3 power n and the number of boxes one can get as 2 power n. So, if you are fixing delta as 3 power n, then one can observe the number of boxes required to cover the objects is 2 power n. If you are finding the box counting dimension for here, then ln of 2 power n over 3 power n. So, finally, one can get d is ln 2 by ln 3, which is less than 1. The Cantor set C is embedded in the space R, or more precisely C is embedded in the set closed interval 0, 1. Both the closed interval 0, 1 and the real numbers, if you are finding the dimension d which is equal to 1, then the comparison between the dimension of the Cantor set and the dimension of the embedded space, then ln 2 by ln 3 is strictly less than 1. Therefore, one can conclude that the Cantor set has a fractal nature, and we can call this as the example of a fractals. We already committed that the Cantor set has a self-similar property. Now, its fractal dimension is less than 1. You can take any arbitrary small part of this object, it has the fine structure. You will not find any smoother part whenever you are taking, in whether zoom in and zoom out, you will not get the smoother part. Also, it made up by finite copy of itself. Therefore, the Cantor set is a classical example for the fractals. Now, let us verify the self-similar property, as we already verified for the self-similar property for the Sierpinski triangle. Let us try to find the box counting dimension of Sierpinski triangle. For finding the box counting dimension of the Sierpinski triangle, we started with the equilateral triangle. I just recall it. We divide each side as 1 by 2, then you can assume that the side length is 1, and we divide each side as a 2 equal part and joining the mid part. So, after the first iteration, we will remove this interior without boundary. We have 1, 2, 3 triangles which has the side length 1 by 2. So, after the first iteration, if you are taking delta as 1 by 2, the number of triangle, here the box it means the triangles. The triangle is required to cover this object is 1, 2, 3. So, if you are observing from the previous process of obtaining the fractal dimension for the Cantor set, here also the box counting dimension of the Cantor set in the first iteration ln 3 number of boxes required to cover the object over boxes of size delta. So, here delta is 1 by 2. So, 1 by 2 inverse will get ln 2, which is less than 2 but greater than 1. So, after the first iteration, for finding the fractal dimension, we need to find the covers. For the covers, I am fixing the delta as 1 by 2. That means box size as 1 by 2. The number of boxes required to cover the object is 3. Then by using delta and n of delta, we can find the fractal dimension. It is ln 3 by ln 2. It is lies between 1 and 2. This is the after the first iteration. After the first iteration. So, after the second iteration, if you are choosing delta as 1 by 2 power 2, then number of boxes required to cover the Sierpinski triangle after the second iteration. This will produce 3 subtriangle, this will produce 3 subtriangle, this will produce 3 subtriangle, then the number of delta one can get 3 power 2. We need 9 boxes of sizes 1 by 9 to cover the Sierpinski triangle in the second iteration. So, if you are finding a d value here, then one can get the same value ln 3 by ln 2, the 2 will cancel. Again, whenever you are taking the delta values 1 by 2, 1 by 9 or 1 by 27, in general, if you are taking delta is 1 by, after the nth iteration, we have box sizes 1 by 2 per n. If you are choosing, then the number of boxes required to cover the Sierpinski triangle in the nth iteration, n of delta one can get 3 power n. So, then box counting dimension, which equals ln of 3 power n over ln 2 power n, which is equals ln 3 over n ln 2 is equal to ln 3 by ln 2. This n will cancel, one can get ln 3 by ln 2. If limit n tends to infinity, we will get the Sierpinski triangle. So, if you are, one can choose the delta as 1 by 2 power n, then the number of boxes 3 power n we require to cover the Sierpinski triangle. So, the box counting dimension or fractal dimension of the Sierpinski triangle is ln 3 by ln 2, which is less than 2, obviously greater than 1. And one can note that this Sierpinski triangle is embedded in R power 2. If you are finding the box counting dimension of the set R power 2, which is equal to 2, which already we discussed. Now, the Sierpinski triangle's box counting dimension is ln 3 by ln 2. So, ln 3 by ln 2 is less than the 2, which is the embedded space fractal dimension. One can conclude that Sierpinski triangle is also a fractals, since it possesses a self-similar property and it has a non-integer fractal dimension. Also, if you are taking any smaller part, you will get the fine structure, as well as you will never find the smoother part. You will never find the smoother part. So, this is also one of the classic example for the fractals. Let us try to find the fractal dimension of the Van Koch curve. So, how we constructed this Van Koch curve? So, Van Koch curve, we take the unit line dividing as 3 equal part. Here we make it as a side of an equilateral triangle and we remove this one. We make this as a side of an equilateral triangle. So, after the first iteration, we have how many line segment? 1, 2, 3, 4 line segment of size 1 by 3. Since we started with the unit interval dividing 3 equal parts, so each has size 1 by 3. So, if you are choosing delta as 1 by 3, then the number of delta is required to cover this object is 1, 2, 3, we need 4. So, as per the definition of fractal dimension, one can get ln 4 by ln 3 as the dimension of the first iteration, which is also less than 2. The next process will get here will produce 4 line segment, this will produce 4 line segment, this side will produce 4 line segment and this side will produce 4 line segments. So, 1, 2, 3, 4, each will produce 4 segment. So it has the 16 number of boxes of size delta is 1 by 3 power 2. If you are taking delta is 1 by 3 power 2, then number of boxes is required to cover the Van-Koch curve in the second iteration is 16. So if you are finding the d value, it is ln 4 power 2 by ln 3 power 2, which is equal to ln 4 by ln 3. In the same way, after the nth iteration, Sierpinski triangle has 4 power n line segment of length 1 by 3 power n. Hence, if you are fixing delta as 1 by 3 power n, then the number of boxes required to cover the Sierpinski triangle in the nth iteration is 4 power n. So then one can get the fractal dimension or box counting dimension of the Sierpinski triangle when n tends to infinity, n limit ln 4 by ln 3, which is less than 2. Similarly, this Van-Koch curve, like a Sierpinski triangle, this also embedded in r power 2. Then, as we already know, this has a box counting dimension 2, and the dimension of Van-Koch curve we obtained as ln 4 by ln 2, ln 4 by ln 2, which is less than the embedding space box counting dimension, which is r power 2 equal to 2. Therefore, we can conclude that Van-Koch curve also a example of a fractals. Why? It has a self-similar property and its box counting dimension is non-integer, and if you are taking any smaller part, it is a fine structure and you will not find the smoother part. Whenever you are zoom in or zoom out, you will get the same pattern at arbitrary all the scales. So it possesses all the property. Therefore, this is also example of a fractals. And now we obtained the box counting dimension of the line segment, which we obtained as 1, and if you are taking the unit square, then the box counting dimension is 2. For the Cantor set, the box counting dimension is log 2 by log 3 or natural logarithm, then you will get 0.6309, and the Sierpinski triangle, the value is 1.5849 approximately, and Van-Koch curve, the fractal dimension is 1.2618. Now, these two objects, Sierpinski triangle and Van-Koch curve, both are embedded in r power 2, and both has the box counting dimension less than this r power 2. So, both are the example of fractals. This one is embedded in R, this box counting dimension is lesser than the embedded space box counting dimension. Therefore, this Cantor set also a example of an fractals. So, in this lecture, we define what is an fractal with respect to two definition. One is based on the dimension, another one is based on the self similar property. Based on the dimension, a set has a Hausdorff dimension which is strictly greater than its topological dimension, and it is called as a fractal, whereas we obtained the fractal dimension for all the objects and compared with it embedded space fractal dimensions. So, if you want to confirm the object is fractal, both are equivalent way to say the object is fractal. The Hausdorff dimension and finding the topological dimension If this is greater than this one, the object we can call it as fractal. Alternatively, for an object and the embedded space, you can find the fractal dimension. If the embedded space fractal dimension is greater than the object's fractal dimension, then object has the fractal nature. This is the one way. And other way, if you are taking the shape and part of that shape is resemble the whole, then we can call it as an object as a fractal nature. But one point you must note that here all the Euclidean object obviously has the self similar nature. Line, square, rectangle, circle, spheres, you can take anything. You can take the part of that, it will exactly resemble the same. So, almost it has the exact self similar nature in the Euclidean objects. Whereas, if you are finding the fractal dimension for this object, we can get the same as its embedded space dimensions. So, this is the one easiest way to understand or define the fractal. Thank you.